Hello, my name is Maria Blasi and I am presenting joint work with George Korakakis from the Department of Graphic Design and Visual Communication at the University of West Attica and Costandina Dalla Costa. Today I will present the design of interactive, simulation-based laboratories for teaching pre-press color management in technical and first-year higher education, an openly accessible, browser-based platform that makes the hidden logic of color management visible to learners. Color management is a foundational competency in graphic arts education. Yet, in professional workflows, the conversion from RGB to CMYK happens inside color management modules using three-dimensional lookup tables embedded in ICC profiles. These systems are effective, but they are black boxes. A student gets a CMYK value for an RGB input but cannot see the conversion to CIE lab, the gamut boundary detection, the chroma compression, or the black generation strategy behind it. This opacity has two educational costs. First, it produces procedural knowledge. Students learn which buttons to press without the conceptual understanding needed to diagnose problems and adapt to new technologies. Second, from a cognitive load perspective, when numbers such as CIE lab coordinates and delta E tolerances are separated from their visible consequences, learners split their attention between abstract parameters and software outputs. According to the cognitive load of multimedia learning, this extraneous load directly hinders the construction of coherent mental models. The evidence for simulation as a response is strong. Radden and colleagues showed that simulations enhance science instruction when learners manipulate variables and observe the consequences. Brinson found that in 89% of comparison studies, learning outcomes in virtual laboratories equaled or exceeded traditional hands-on laboratories. A meta-analysis of 145 studies by Herikova and colleagues reported a large overall effect for simulation-based learning in higher education. Other researches showed that inquiry works best when it's guided. These four findings shaped our design. However, the prepress domain is underserved. Professional tools are accurate but opaque. Commercial courses are passive, and open color science tutorials stop short of print production. So, we asked three questions. First, how can prepress colorimetric processes be represented through transparent, interactive simulations? Second, to what extent can heuristic modeling approximate ICC-based transformations for educational purposes? And third, how does algorithmic transparency align with established principles of cognitive load reduction? Our answer is a strictly client-side web application, HTML5, CSS, and JavaScript. that runs in any modern browser without installation or registration. Instead of interpolating measured lookup tables, every conversion is performed by lightweight heuristic models in CIE-lab space, so the logic itself is inspectable and modifiable. The work is framed as a design and development study. The platform is open source under an MIT license, permanently archived on Zenodo with a DOI, and freely available at the links shown. The environment consists of 9 self-contained laboratories that move from foundational to complex phenomena, implementing Mayer's principle. Each laboratory isolates one calorimetric concept. Let me walk you through the key ones. Laboratories 1 and 2 externalize the physical distinction between additive and subtractive color. RGB values are first converted to linear light before the channels are added, while inks are modeled as broadband filters. A live spectral absorption graph shows why overlaying all 3 pigments never produces an ideal black. Laboratory 3 separates any color into its 4 printing channels rendered as half-tone rosettes at the standard screen angles that prevent moire interference. Laboratory 4 computes total area coverage in real time and produces visible smearing artifacts when the substrate heat limit is exceeded. Laboratory 5 plots gamut boundaries on the chromatical diagram, and Laboratory 6 demonstrates gray component replacement across 5 levels. Laboratory 7 addresses dot gain. An inspired teaching model by Murray Davis and Yunil Nielsen generates tone value increase curves for coded, uncoded, and newsprint-like conditions. A movable cursor lets students query the apparent printed tone for any digital file tone in real time. Laboratory 8 is the heart of the platform. The same input color is mapped side by side under all 4 ICC rendering intents with live delta E readouts. The gamut boundary is approximated by a continuous function of lightness. Printable chroma peaks in the mid-tones and collapses at the tonal extremes. Out-of-gamut colors are compressed towards the boundary, while hue and lightness are preserved, and black point compensation is modeled after Adobe's published approach. Because the model is an equation rather than a table, students can see it, discuss it, and even modify it. Laboratory 9 introduces proof evaluation. The computed CIEDE 2000 difference between the screen color and the simulated print is checked against a single pass teaching threshold of 3, while making clear that this is instruction about proof assessment, not certified contract proofing. Every laboratory carries an integrated scientific companion, learning objectives, theoretical background, inquiry prompts, self-check activities, and local observation notes. A technical notes section documents every modeling simplification, turning the approximation boundaries into visible learning content. The heuristic is compared with Adobe Photoshop's color engine. 10 sRGB samples, neutral grays, skin tones, and saturated colors were converted to ISO-coded version 2 with perceptual intent and black point compensation, and compared with the platform's teaching mode output. We stress that this is a consistency check of the educational model, not a claim of metrological equivalence. The engine reproduced exactly the categorical behavior we teach. Every in-gamut sample passed through unchanged with a delta E of 0. Slightly out-of-gamut samples received moderate compression between 3.7 and 6.2, and extreme out-of-gamut colors were strongly compressed up to 26.4. In other words, the model distinguishes printable from unprintable color and intervenes only when needed. To conclude, by replacing lookup tables with inspectable equations, hidden processes become visible, manipulable, and discussable at zero cost in any browser. The limitations are explicit. The boundary model ignores hue-specific asymmetries. The engine works purely in CIE lab, and we have not yet measured learning outcomes. A pre-test and post-test classroom study combined with technology acceptance measures is the next research phase. Thank you for your attention. The platform, the source code, and the archived release are available at these links. Please try the laboratories yourself directly in your browser. We welcome your questions and feedback at the addresses shown.